let's look at an additional example of finding volume using really integrated integrals. So I've got some region, and it's bounded by the xy plane and this paraboloid, 4 minus x squared minus 2y squared. So I have a paraboloid, so I might have to ask myself, is that going to be a paraboloid that opens upward? Is it one that opens downward? Or is it a hyperbolic paraboloid, so it kind of has a little bit of both? Well, if you look at this, this is an elliptic paraboloid because these have the same sign. And if you think about it this way, think about for values of x and values of y. If they're both 0, z is positive. But no matter what I plug in for x or what I plug in for y, the squareds on these will make those positive, and then the negatives will make those negative. So you start at 4, and then you're gonna have this elliptic paraboloid that just folds down. So I start at 4 and I fold down, and I'm going to hit the xy plane. So I need to solve this, what I need to do is I need to find the bounds of my integration, or find my limits of integration, and then we'll be able to integrate the volume. So a very, very rough sketch of what this might look like is something like where it starts up here and kind of has that elliptic paraboloid shape. So we want to have that sort of bell-ish type shape. We want to find the volume of that bell. So let's go ahead and start looking at this. The first thing we always want to do is we always want to find the bounds. And so we know that it strikes the xy plane. The z value has to be equal to 0. So that tells me that for this particular case, we're going to take that level curve where z equals 0. We're going to look at that level curve. So rewriting this, we get x squared plus 2y squared equals 4. Another way that you might write this would be, x squared over 2 squared plus y squared over the square root of 2 squared equals 1. That's an ellipse. And if you remember how ellipses work, is you have your semi-major and your semi-minor axis. And this is going to be your semi-major axis because it's going to go out further. So x then will go from -2 to 2. But what will y go to? Well, the way you want to do that is you want to solve this equation. So if I solve this for y, what I get is, so I have x, let's leave this alone. So we have x squared plus 2y squared equals 4, or 2y squared equals 4 minus x squared, or y squared equals 4 minus x squared over 2. So y is plus or minus 4 minus x squared over 2. So what that tells me is y can get for whatever x value is, y can get no smaller than -4 minus x squared over 2, and it can get no larger than 4 minus x squared over 2. So that's kind of the idea here. Okay. All right, now we have these bounds here. Let's evaluate the integral. So we want to use the iterated integral form. -2 to 2, negative square root of 4 minus x squared over 2, to positive 4 minus x squared over 2, so just these bounds, of this function. Okay, well, when we integrate that, so we're going to get 4 minus x squared times y minus 2/3 y cubed. But before we do that, let me take a step back. So there's a property of what's called an even function. Even functions happen when if you plug something negative in, you get the same output as if you plugged a positive number in. Well, if you look here, in terms of y, these are constants which don't affect whether or not a function is even. And this has a y squared. So if I plugged a negative value in or a positive value, the squared takes care of the negative. So this is an even function. Even functions have an interesting property that if the bounds on top and bottom are the same number, but that one's negative and one's positive, basically you have a mirrored or symmetric interval. You can say, okay, well, since it's the same on the negative side as the positive side, I can look at just the positive side and double my answer. So we can say that's really just double the answer of this case. And the reason why we want to do that is because that's going to make evaluating this next piece a lot more straightforward. Because when I plug in 0 for these pieces, they go away. So I only really have to worry about that top piece. Okay, so let me talk about this for a second. So when I plug this in here, I already have 1 4 minus x squared, but I get another 1/2, so this becomes 4 minus x squared to the 3/2. And then that 1 over square root of 2 comes out. Over here, I have to cube it. So this is like 1 over 2 to the 1/2. So that's 1 over 2 to the 3/2. And then the top piece was to the 1/2, so it becomes also to the 3/2. But then I also have this negative 2/3 in this piece over here. So I need to, these are the same, which is the whole point, but I need to take care of these coefficients. So 2/3, well, 2 to the 3/2 is 2 square root of 2. So that's 1 over 3 square root of 2. So I have 1 over square root of 2 minus 1 over 3 square root of 2, which is to say, that's sort of like saying square root of 2 over 2 minus square root of 2 over 6, which is 3 square root of 2 over 6 minus square root of 2 over 6, which is 2 root 2 over 6, which is square root of 2 over 3. So we pull all that out here. So now I have 4, or the 2 that I had, square root of 2 over 3, times the integral negative 2 to 2, 4 minus x squared to the 3/2 dx. Whew, a lot of work here. But we're not done. Ugh. So this is also an even function. 4 minus x squared no matter what I plug in for x, negative or positive, I get the same output. So I can then convert this to 4 square root of 2 over 3 from 0 to 2, 4 minus x squared to the 3 halves dx. I'm going to change gears for a moment. We're going to do a trigonometric substitution. We're going to say x equals 2 sine theta. So dx is 2 cosine theta d theta. When x is 0, sine of theta, or theta must be 0 because sine of theta is 0. When x is 2, 2 equals 2 sine theta, so theta must be pi over 2. So now we have 4 square root of 2 over 3, 0 to pi over 2, 4 minus 2 sine theta squared to the 3 halves times 2 cosine theta d theta. So then that becomes 8 square root of 2 over 3, 0 to pi over 2, 4 minus 4 sine squared theta to the 3 halves, cosine theta d theta. Well, if I factor a 4 out and take it to the 3 halves, that's another 8. So that becomes 64 square root of 2 over 3, 0 to pi over 2, of 1 minus sine squared theta to the 3 halves, cosine of theta d theta. So then 1 minus sine squared is cosine squared. And cosine squared to the 3 halves is cosine cubed. And cosine cubed times cosine is cosine to the 4th. Okay, well, I'm gonna stop here. And the reason being is because this right here, you have to do, apparently there's a formula for it. I didn't really ever know, but what you find is like something like cosine squared theta is 1 plus cosine 2 theta over 2. I believe that's right. Yeah. And so then cosine to the 4th of theta is equal to 1 plus cosine 2 theta over 2 squared, which then will get you 1/4 1 plus cosine squared 2 theta plus 2 cosine 2 theta. And those two are directly integrable, but then you have to use this formula again to get something in terms of 4 theta, and it just keeps on going and going and going. And so, in the interest of time, what I originally had when this all came out was something like 4 square root of 2 pi. And there may be some issues here that don't lead you to this answer. But the key here is not any of that. The key here is understanding how to find bounds, how to set up an integral, how to walk yourself through the integral, knowing that, sometimes it's going to get nasty. Like, I'm no way around it. It's going to get nasty. You just have to kind of lean on your calculus skills and just go at it. Just like in regular calculus, differentiation is fairly easy. Integration can be decently hard. So just keep practicing and it'll come to you.